Good afternoon, my name is Juliana Siebel, and I work with the Levy Lab at the University of Pittsburgh. Today I'll be discussing transport measurements using whole cross geometry to probe the electronic structure of graphene nanoribbons. One goal of Levy Laboratory is to measure the electrical properties of materials at ultra-low temperatures and occasionally high magnetic fields. As a lab interested in quantum computing, we are interested in investigating the quantum properties of molecular scale systems that may one day be used to build quantum computers. A quantum computer controls a large number of quantum mechanical objects called qubits, and as we are particularly interested in spin-based quantum information, we want to be able to control the spin orientation of each individual electron and also couple spins together. We propose graphene nanoribbons, or GNRs, as a strong contender for this application as a qubit. GNRs stand out to their bottom-up atomic precision and great variety with which they can be synthesized. Our motivation is to develop a spin-based qubit that will be within a graphene nanoribbon. GNRs are tiny strips of graphene, about 1 nanometer wide and 10 to 50 nanometers long. GNRs are important candidates because of their atomically precise chemistry, which can be controlled with the precision of every atom during chemical synthesis. GNRs often have energy band gaps, and their electronic structure depends sensitively on their width and edge geometry. We want to use transverse electric fields to induce band gaps in GNRs that are metallic, so when the electric field switches signs, you get localized quantum dot-like states, and this is what we're most interested in developing. A senior lab member, Aaron Sheridan, has studied GNRs using optical techniques, but here we want to focus on transport measurements. To probe the GNRs, we will use the lanthanum aluminate strontium titanate, or LAO-STO heterostructure. This complex heterostructure is filled with a lot of interesting physics, but here we're going to work with LAO grown on top of STO exactly at the critical thickness. This way, one can reversibly tune the conductivity of the interface. In our group, we've developed a method to modulate this metal insulator transition at the nanoscale using conductive atomic force microscope lithography, or CAFM lithography. How this works is we start with LAO grown on top of STO at the critical thickness. Contacts are fabricated that have contact to the interface. We then bring a conductive AFM tip into contact with the surface of the LAO. When we apply a positive voltage to the tip, it effectively deposits protons on the surface of the LAO, and these in turn attract electrons to the interface, locally modulating the metal insulator transition. Similarly, when we apply a negative voltage, we effectively remove the protons we deposited, erasing the conducting nanostructure. And using this method, we're able to create nanostructures as small as 2 nanometers in size at room temperature. That leads to the likeliness of an etch-a-sketch technology, but truly at the nanoscale. And so using this method, we can create a diverse array of devices. I'll briefly discuss 3 types of electronic devices that we can create on the LAO-STO platform using AFM lithography. Then I'll show how we can incorporate GNRs and study their electronic structure. I'll discuss the single electron transistor, the ballistic electron waveguide, and then finally the nanocross. Starting with the single electron transistor, here we see a quantum dot, which is more like a dash in size in this paper. A positive tip bias is used to connect the source and drain electrodes, and the island is created by making 2 perpendicular cuts to the nanowire using a negative erase voltage. The quantum dot is isolated by insulating barriers, and there's an electrical side gate that tunes the chemical potential of both the upper wire and the quantum dot. It modulates the tunnel coupling between the quantum dot and the external leads. We want to control and see how many electrons are tunneling across these insulating barriers to inhabit the island, and sweeping a gate allows us to tune the chemical potential to allow electrons to tunnel onto the island when the chemical potential of the source matches that of the island. When the chemical potential of the source leads are between an occupied and unoccupied state, you get Coulomb blockade. An electron cannot fill the next state due to the chemical potential not being large enough to match that of the island. When the chemical potential of the source is raised to the next state, electrons are able to hop onto the island to occupy this next state. Differential conductance versus side gate voltage measurements for the quantum dot exhibit a sequence of diamond-shaped insulating regions for specific side gate voltage values. Coulomb diamonds help identify the addition energies. The nodes are the regions where you have resonant transition, and the diamonds open to the blockade regions. Next, we look at the waveguide geometry, which consists of a long, narrow main channel that's separated from source and drain electrodes by insulating barriers. It's different from an SET because the barriers are created in line by modulating the tip voltage, whereas for an SET, the barriers are written perpendicular to the main channel, giving stronger confinement. For the waveguide, a current is sourced from one lead, and the side gate applies a voltage to influence the conductance through the main channel. The conductance will depict the number of accessible quantum channels, and the side gate tunes the chemical potential and allows electrons to tunnel across the barriers, and as the chemical potential is increased, electrons can occupy more subbands. Incorporating a magnetic field will shift the energy in the subbands due to Zeeman and orbital effects, and looking at the conductance as a function of side gate voltage, we see these quantized steps in intervals of E²/h. We have noticed some puzzling features in our data from our SET devices, which I'll discuss next, and the nanocross's properties hold promise to help us overcome this. A nanocross device consists of two cross-electron waveguides created using the technique that I explained in the previous slide. By crossing the two waveguides, the structure has been shown to produce highly reproducible data, such as in this paper. The device's reproducibility is believed to be due to the ferroelastic domains in STO. At 105 Kelvin, STO undergoes a structural phase transition from the cubic to tetragonal state and forms X, Y, and Z ferroelastic domains along the crystallographic directions. The domains are sensitive to applied force and strain, and hence known as ferroelastic domains. It's been shown that the X and Y domains share a similar surface potential, and the Z domains have a higher surface potential. Thus, the Z domains in STO can be argued to form the conducting regions at the interface, where the X and Y domains define the insulating states. There are also domain tiling rules, which dictate how the domains form next to each other. Due to the conductivity affecting the domain structure, the electrical properties of the nanocross are highly reproducible. Next, we want to study how each of these devices gets modified by the presence of a GNR. Starting with the SET device, the GNRs are placed on the sample surface, co-located with the SET island, and to study the addition energy, or sense the extra electron that goes onto the GNR, we expect to see shifts in the conductance peaks to the right and to the left as the SET acts as a charge sensor. By sensing the charge presence, this can tell us about the electronic structure of the GNR, assuming we know the electronic structure of the quantum dot. And this is the current challenge, being able to differentiate those two effects. For the waveguide device, the idea is similar. We expect a change in where the conductance jumps from one state to another, and we should be able to differentiate characteristics in the transconductance of the GNR from the LAO-STO properties. And then similarly for the nanocross, placing a GNR near the nanocross will modify the energy structure. Because they are highly reproducible, we can then compare the transport properties of LAO-STO with and without a GNR, and we should be able to see the gating effects from the GNR. I have been creating SET and waveguide devices to try to create reproducible signature in these devices, and in the transport data here, we have a GNR coupled to an SET. We see these large oscillations and also the inability to tune the device to values greater than 2.6 E²/h of conductance. And this data is complex, so it's been difficult to separate out the behavior of the GNR from the behavior of the device. And this is why we hope the nanocross design properties will help. In conclusion, we propose to develop a new spin-based qubit based on the unique atomically precise properties of graphene nanoribbons, combined with the nanoscale reconfigurability of the LAO-STO system. The LAO-STO system provides a platform for many electronic devices, and using the nanocross geometry, we hope to get reproducible transconductance plots to differentiate between the behavior of the two effects to extract information about the GNR structure. This will be the gateway to then utilizing a single electron transistor to study the addition energies to try to probe the electronic properties of GNRs. And with that, I'd like to thank you for your time. Please go make sure to take a look at some of the other talks from our group. Thank you.